Hello everyone. Let us continue with our discussions on hydrogen. In the last class, we have seen two types of hydrides that are formed by hydrogen. The first one was ionic or saline hydrides, and the second one was covalent or network hydrides. Now the third type of hydrides that are formed by hydrogen are these metallic hydrides or interstitial hydrides. These are also called as non-stoichiometric hydrides. Now, many of the D block and F block elements react with hydrogen to give metallic hydrides. However, metals from groups 7, 8, and 9 do not form hydrides. Unlike saline hydrides, these metallic hydrides, they are almost always non-stoichiometric, being deficient in hydrogen. So they are known as non-stoichiometric hydrides. For example, lanthanum hydride, as this formula suggests, for each hydrogen there should be one lanthanum, or the hydride of lanthanum actually is LaH3. So this formula suggests that for each lanthanum atom there should be 3 hydrogen atoms. But in the actual molecule, we find that the ratio of hydrogen to lanthanum, which actually should be 1:3. The ratio of lanthanum to hydrogen atom should be 1:3 as suggested by this formula. But if we see the actual molecule, the ratio is found to be 2.87. Not exactly 1:3, it is 2. This should be 1:2.87. So this is less than 3. That means in the actual molecule, the ratio of the different atoms in the molecule is not the same. Therefore, this kind of hydrides, they are called as non-stoichiometric hydrides. Now, earlier, it was thought that in these hydrides, hydrogen occupies interstices in the middle lattice, the vacant spaces in the middle lattices, without changing the original crystal structure of the middle. That is why they are also called interstitial hydrides. However, recent studies have shown that except for hydrides of nickel, palladium, cerium, and actinium, other hydrides of this class have lattices that are different from that of the parent metal. Okay, that is all about the different types of hydrides that are formed by hydrogen. Now let us see some compounds that are formed by this hydrogen. Water, that is H2O, and hydrogen peroxide, H2O2, are two very important compounds. These are oxides of hydrogen, and we will see them a little about these two compounds one by one. Now, water, it is a major part of all living organisms, and the human body has about 65% of water, and some plants have as much as 95% water. Now, it is a crucial compound for the survival of all life forms, and it is a solvent of great importance. About 75% of the Earth's surface consists of water, but unfortunately, most of the fresh water is not readily available for human consumption because they are locked up in frozen lakes, glaciers, or underground. Only about 0.003%. Only about this much of water is readily available for human use. Now, if we see the physical properties of water, it is a colorless, tasteless, and odorless liquid, and the freezing point, boiling point, enthalpy of fusion and enthalpy of vaporization are higher as compared to hydrides of other members of the same group, such as hydrogen sulfide, etc. This is due to the presence of intermolecular hydrogen bonding in water molecules. If you take H2As and H2O, water. These are hydrides of the same group of elements. Oxygen belongs to group 16. Sulfur also belongs to group 16. Now, if we see the hydrides of these two elements, oxygen and sulfur, since they belong to the same group, their hydrides should have similar properties. That is what we would expect. But we find that hydrogen has much higher boiling point than this H2S gas. Water has higher boiling point than H2S gas. And the reason why this is so is because hydrogen bonding takes place in water molecules, but hydrogen bonding is not possible in this hydrogen sulfide. Not only that, due to hydrogen bonding, this water exists as a liquid at ordinary temperatures, but H2S exists as a gas under room temperatures. Because of the absence of hydrogen bonding, the only forces that hold the H2S molecules together will be the weak van der Waals forces. Therefore, at room temperature, it exists as a gas. But due to hydrogen bonding, water exists as a liquid at room temperatures. Water has higher specific heat, thermal conductivity, and dipole moment in comparison to other liquids. These properties allow it to play a key role in the biosphere. It has high heat of vaporization and heat capacity, which are responsible for moderation of climate and body temperature of living beings. So the property that is responsible for moderation of climatic temperature and body temperature of living beings is its high heat of vaporization and its high heat capacity. Due to hydrogen bonding with polar molecules, even covalent compounds like alcohol and carbohydrates are dissolved in water. We have a saying that like dissolves like. Covalent compounds are soluble in covalent solvents. Ionic compounds are soluble in ionic solvents. But water, which is an ionic solvent, can dissolve organic compounds also. And the reason is because these organic compounds, covalent compounds, some of them they are able to form hydrogen bonding with water molecules. And that is why they are soluble in water even though it is an ionic solvent or a polar solvent. Now, water exists in nature as solid, liquid, as well as gas. So, in nature, water can be found in all the three states of matter, that is, as a solid, a liquid, as well as a gas. If we see the structure of water, in the gaseous phase, water is a bent molecule with a bond angle of 4.5 and OH bond length of 95.7. So water in the gaseous state has this structure, a bent structure or a V-shaped structure in which the bond angle here is 104.5 degree, and the distance between this oxygen and hydrogen atoms, both these bonds are the same, and the distance is about 95.7. So this is how water molecule exists in the gaseous state. In the liquid phase, water molecules are associated by hydrogen bonds. Each oxygen can form two hydrogen bonds with utilizing both lone pairs in it. So in the gaseous phase, the water molecules will be far apart from each other and each molecule will exist in this form. But in the liquid state, these H2 molecules, they are bound together by hydrogen bonds like this. So if we just see the structure of water in the liquid state, each oxygen can form two hydrogen bonds. Each oxygen atom can form two bonds, hydrogen bonds, utilizing both the lone pairs in it. Now, oxygen, it has 6 electrons in the valence shell. Out of these 6 electrons, 2 are shared with the 2 hydrogen atoms to form 2 covalent bonds. After the bonds are formed, 4 electrons remain in the valence shell of oxygen, and these exist as lone pair of electrons. So in the liquid state, the water molecule, the oxygen atom utilizes both this lone pair of electrons to form hydrogen bonding with hydrogen atoms from other molecules. So all the water molecules will be joined together by hydrogen bonds like this. Ice, which is the solid form of water, can exist in different crystalline forms depending on the conditions for freezing the water. At atmospheric pressure, it crystallizes in hexagonal form, but at very low temperature, it condenses to form a cubic structure. So depending on the conditions that are used for freezing up the water to form ice, the structure of ice will be different. So at atmospheric pressure, it will crystallize to form hexagonal structure. But when the temperature is kept very low, it will condense to form cubic structure. In the normal hexagonal ice, each oxygen atom is tetrahedrally surrounded by 4 other oxygen atoms. Let us see the structure of ice when it is in the hexagonal form. So if we just see this structure of ice, we will find that each oxygen atom will be surrounded by 4 other oxygen atoms through hydrogen bonding like this. Each of these oxygens again will be surrounded by 4 others. So this is how a tetrahedral arrangement is formed between the water molecules, between the H2O molecules. So each hydrogen is covalently bonded to 1 oxygen atom. Each hydrogen is bonded covalently to 1 oxygen atom and linked to other oxygen atom by a hydrogen bond. So if you just see this hydrogen, this is covalently bonded to this oxygen, and to this oxygen it is linked by a hydrogen bond. Such an arrangement leads to a packing with large open spaces. The density of ice is therefore less than that of liquid water, and that is why ice floats on water. Ice floats on water because it has less density than the liquid water. Now during winters, when the temperature falls below 0 degrees Celsius, in aqueous bodies such as lakes, the upper layer gets frozen to ice. The floating block of ice prevents or delays the freezing of the underlying water. This enables aquatic life to survive during winter months. Suppose we have a lake with a lot of water here. During winter months, due to the very low temperature, this water gets frozen. Once the water gets frozen, what happens is the ice that is formed here, since it is lighter than the liquid water, it will float on the surface of the water. And this acts as a blanket that prevents the underlying water, the water that is inside, from freezing out. It does not allow the cold wind to enter inside and acts as a blanket. So the water inside does not freeze up. And that is how the aquatic life inside the water survives during the winter months. Now, let us see some chemical properties of water also. If we look at the chemical behavior of water, water shows a versatile chemical behavior. It acts as an acid, as a base, an oxidizing agent, a reducing agent, and even as a ligand to metal ions. So it has a very versatile chemical behavior. Not only does it act as an acid as well as a base, it can act as an oxidizing as well as reducing agent, and even as a ligand to form complexes. Now, water is said to be amphoteric. Amphoteric nature means that water can act as an acid as well as a base. Now, if we just take 2 examples here, water reacts with ammonia to form this hydroxide ion and ammonium ion. If we see this reaction, water gives out one proton to NH3. It donates a proton, and therefore it acts as an acid in this reaction. After donating one proton, a hydrogen ion as a proton, it forms OH ion, the hydroxyl group, and NH3 after receiving becomes, the hydrogen ion becomes NH4, the ammonium ion. So in the reaction, water donates a proton to ammonia, and therefore it acts as an acid. Now in the reaction, water reacting with hydrogen sulfide, we get this H3O and HS. Now if we see this reaction, we will find that water has received one proton from H2S gas, and it has formed this H3O. So in this case, water accepts a proton, and therefore it acts as a base. So in different reactions, water can act as acids. In other reactions, it can act as base also. That is why water is said to be amphoteric. Amphoteric means it behaves as an acid as well as a base. Then if we see the next type of reaction, that is the redox reactions. Redox reactions are those reactions in which oxidation as well as reduction takes place simultaneously. So water can be reduced to dihydrogen by highly electropositive metals. Water is treated with a highly reactive metal like sodium, then it gets reduced to form sodium hydroxide. The metal reduces water to form sodium hydroxide. Then in the next reaction, it undergoes oxidation. When reacted with carbon dioxide, it gets oxidized to form glucose, water, and oxygen. So in this reaction, water gets oxidized. In the first reaction, it gets reduced. When it gets reduced, it acts as an oxidizing agent. When it gets oxidized, it acts as a reducing agent. So from these reactions, we find that water can act as an oxidizing as well as reducing agent. That is all for today. We will continue in the next class.